Dear learners, welcome to week 6, lecture 2. In this lecture, I will explain the first free vibration solution of all round simply supported finite cylindrical shell, and then state of art for developing Levy type boundary conditions finite shell. Previously, I have developed Navier solution for static bending and approximate solution for arbitrary supported cell panels. The geometry remains same. A finite cell panel is considered. Coordinate first direction is x, second direction is theta and z. Z is our radial directions, basically thickness direction. The displacement field is same. Now we are directly coming to the governing equations. These governing equations we have derived in last lectures, basically week 5 lecture and L1 and L3. This time I am including the dynamic terms also. First I will number these equations. Number 1 equation, number 2 equations, and this equation is number 3, number 4 equation and number 5 equation. And these are the boundary conditions. At the x is equal to 0 and a, the following variables need to be specified. At theta is equal to 0 and psi, these variables need to be specified. Just for the sake of completeness, I have given again the definition of stress resultants, moment resultants and shear resultants and the loading. These are required for the present case. So, I have rewritten the cell constitutive relations which we have derived in week 5 lecture 3. nxx, n theta theta, nx theta, n theta x. Here you can see that they are expressed in terms of primary variables psi u1 0 comma x, u2 0 comma theta, psi 1 x, psi 2 comma theta and so on. Similarly, the moment mxx, m theta theta, mx theta, m theta x, qx and q theta are represented. I have numbered this equation 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, we have 10 cell constitutive relations. Now, the inertia matrix, the definition of I0. The definition of I0 is minus h by 2 to plus h by 2 rho 1 plus zeta by r1 into 1 plus zeta by r2 into d zeta. For the present case, in the first direction, radius r1 is infinity, so this term will not contribute. So, if this, let us say for a doubly curved, so this term may exist. For that, if you further open it, so it looks like this complete terms. But for the present case, second term and fourth term will not exist. It will contain rho times 1 plus rho times zeta by r2 into d zeta. So, we will integrate over this. So, this contribution will be taken care by I naught, and similarly the I1, I2 contribution is written. In the I2 contribution, zeta is here. In I3 contribution, zeta square. If it is an isotropic shell, then we can directly integrate and we can write rho times of h or rho times of h square by 2 and so on. But for a composite shell or a laminated shell, each layer may have a different density also, like each layer may have a different reduced stiffness coefficients k times. So, same way each layer may have a different density. It may be possible. So, for that case, or may sometimes if we talk about a sandwich shell, that core. So, core is very light and face is having stronger material, may have more density. And this is light material, may have low density. So, in that case, rho is a function of kth, means each layer, and zk plus 1 minus zk. So, the first term contribution. Similarly, the second term contribution, third term contribution can be find it out for the case of a composite cell. In this way, I0, I1 and I2 are calculated. Now, using the cell constitutive relations, if we substitute into the partial differential equation, we called it PDE, partial differential equation of shell. So, these are in the 5 number. So, if we substitute all our cell constitutive relations into these, that leads to a equations like this. L is a linear operator, U contains the primary displacement variables U10, U20, W0, Psi1 and Psi2. These are 5 in number. This time you see a dynamic matrix comes into the picture. Let us say a matrix I, just I. So, I11 is your minus I0. I14 is minus I1. I21 is minus I0. So, these are the components of inertia matrix and time derivative of primary variables u double dot 10, u double dot 20, u double dot w0, psi1 double dot, psi2 double dot and load matrix. Basically, it is an column matrix. So, array is written like this. First, I shall explain the free vibration of, because I have already explained the static response of a finite cylindrical shell subjected to all round simply supported case. In this lecture, I shall explain the free vibration of a finite circular cylindrical shell subjected to all round simply supported boundary conditions. For the case of simply supported, a finite shell that along x is equal to 0 and x is equal to a, the variables like w0, u20, psi2, nxx and mxx need to be 0 at the x is equal to 0 and x is equal to a. Theta is equal to 0 and theta is equal to alpha. The variables w is equal to 0, u1 0, psi1 0 and theta theta 0 and m theta theta 0. So, if these variables are specified, then we can assume the solution. Along x axis, w can be assumed in terms of sin m bar x, where m bar is nothing but m pi by a into sin n bar theta. The blue term is for Symmetric case, when loading is symmetric, and where loading is anti-symmetric. Similarly, u1 0 and psi 1, u2 0 and psi 2. Already we are aware about this type of combination, that cos, sin, and the new thing is here the cos omega t, that we have u double dot, w double dot, psi 2 w dot. So, the time, that w in a time domain, it varying cos omega t. Sometimes people used to take e raised to power I omega t, or we can write real part of e raised to power I omega t. So, basically if you open it, it becomes cos omega t plus iota times of sin omega t. So, we are taking only this portion. So, instead of writing in this form, I have directly written that we can assume cos omega t. So, if we take that this is the variation of variable along the in the time domain and the along the space domain, which satisfy the simply supported boundary conditions. If we substitute this Fourier expansion and time expansion into the governing basically P1 equation, we call it is equation number P1, then it reduces to a matrix K, UMN, M matrix UMN and QMN. We will get a matrix like this. The non-zero component of a matrix M1, M3, basically it will be M14, M22, M24, 23, 24, yes, 25, 3, 4, so on. And the stiffness matrix non-zero components are written here. For the case of a free vibration, there will be no loading. So, this equation reduces to equal to 0. So, ultimately M is can be written as minus of I, omega square is common to all. So, matrix I minus of that. So, Km minus I omega square UMN 0 equal to 0. So, this is an eigenvalue problem where this is your mode shapes. So, if we from here Wmn can be find it out, like if it is just a single equation, like in the case of a beam. If it is just a single equation, I can say that omega square is equal to K by I for the case of a beam or a spring. But here Km is a 5 by 5 matrix and I is also a 5 by 5 matrix. So, I can say that I omega square equal to minus Km, minus minus get cancelled out. If I multiply with this I inverse I omega square and K I inverse, so it becomes identity, and in this way 5 different value of omega can be obtained at a time for a particular combination of m and n. Actually m and r Fourier numbers that it may varies from 1, 2, 3, so on. So, let us say for m is equal to 1 and n is equal to 1, we will get 5 frequencies at a time. So, the frequencies corresponding to W naught will be the bending frequency, U10, U20 stretching frequency and shear coupling frequencies. So, for a particular combination of M1 and M2, we will get a bending, stretching and shear modes, the frequencies. So, as we increase that 4, 5, so we will get a infinite set of frequencies. So, for the case of when a cylindrical shell is subjected to all round simply supported, the calculation of frequency is very easy, like a case of a plate. But if we talk about a Levy type support condition, then it is slightly difficult. So, for the Levy type boundary condition, the very first condition is that two opposite edges are simply supported. So, when we say that any structure is subjected to Levy type support condition, in that case we are saying that any two opposite edges, either x is equal to 0 to a or theta is equal to 0 to alpha, is to be simply supported. So, if that is the case, then we can develop a Levy solution. So, in the case of a cylindrical shell, generally along theta direction, that theta is equal to 0 and theta is equal to alpha is considered simply supported. Other axis, which is x is equal to 0 and x is equal to a, can have any combination of the boundary conditions. So, the present case, if we assume that theta is equal to 0 and alpha, that following variables are to be 0. So, if this is the case, we can assume the primary variables in terms of a single series or sine series. So, first case is due to the symmetric loading. So, if we say that loading, in the case of free vibration, loading is not that, but boundary conditions may be symmetric. So, for that case, and if it is a static case, then loading may be symmetry or anti-symmetric. So, we can assume the solution like this: cos and theta if my loading is symmetric, u1 0 cos and theta, u2 0 sin and theta, and so on. And this is the variation of time. Now, substituting this expansion into again P1 gives this big expression. Here one can see that the variation along the theta direction vanishes and it gives you a term that n bar square comes into the picture, and it is simply a u1 0. There is no derivative, but derivative along x axis remains. If I go previously, in this case u1 0 is a function of x, u2 0 is a function of x, w0 is a function of x, psi 1 is function of x. In the case of previous, when all round simply supported, u1 0 mn, u2 0 mn was a constant, just a constant, w0 all. But for the case of if only two opposite edges are simply supported, then these are the function of the remaining variable along the x-axis base. So, if we substitute in that partial differential equation, that gives us a differential equation, but ordinary differential equation in the x coordinate. So, basically it is a second order, highest degree is second order in the first equation also, second equation also, in third equation, fourth and fifth. You will find that second derivative of x and first derivative of x of all the variable exist in equation 1 to 5. So, the solution of this equation can be done by a different ways. One way is that we can directly solve using the some techniques, this second order ordinary differential equations, or if we can convert the most suitable form, basically this solution technique is presented by Khadir et al. In that paper, that these equations are converted into a first order form. First order differential form, ordinary differential equation, the solution is very easy and straightforward. So, we are trying to convert these 5 equations into first order differential equation. Let us see. So, we are defining another set of variable. let us add a variable zm1, that is u10, and another variable zm2 is u10 comma x. So, first derivative is assumed as a variable zm2. Then zm3 is u20 and zm4 is u20 comma x. Zm5 is w0, Zm6 is w comma x, and Zm7 is psi1, Zm8 is psi1 comma x, and 9 and 10. So, in this way we have defined the 10 variables. So, we have 5 equations from here, and we will get the 5 identity equations from this, that Zm1 comma x first का अगर if we take the derivative along x direction, that will be just a variable Zm2. If we take Zm3 comma x, that will be just Zm4. So, in this way we will get the 5 identity equations from here, and in this equation basically u10 will be Zm2 comma x, first order derivative, and this is Zm2. Let me write it, and Zm3 or you can say that Zm4, Zm6, then Zm8, Zm7, Zm9, and here again Zm1 and Zm7. So, we can see that first equation using the concept of another variable z, it is converted to a first order differential equation where highest derivative is along first Zm comma x. So, from this equation, first equation can be rewrite that Zm2 comma x kept one side, and rest of the variable all these can be, because these having no other derivative, only basic, so can be written as, let us say, matrix A into Zm variable u10, u3. Similarly, from here this is Zm2, and second order derivative can be expressed as Zm4 comma x, यहाँ पे 8 comma x. So, in this way again some variables can be done. After mathematical simplification or rearranging, we will get a Z matrix derivative x and A matrix and Z matrix. So, Z contains 10 variables plus the load vector. Again here that concept of I omega square inside, it is taken inside the matrix A. So, this is the first order ordinary differential equation with non-homogeneous, and where A are constant matrix, the solution of this equation is easy. So, this is 10 by 10, 10 cross 1, 10 cross 10, 10 cross 1. So, this is the 10 by 10 matrix. As the standard solution can be written as, let us say Z, any variable can be written as C any matrix e raised to power of lambda into x, where lambda I will explain later on. So, if you substitute this complementary solution, first the complementary solutions. So, complementary solution for the equation can be written as A times into Z. If you substitute it here, it becomes lambda times C e raised to power of lambda x. C is also a matrix equal to A C lambda x. So, if you put it here, so lambda minus A, so ultimately lambda I identity matrix C times lambda x is equal to 0. So, this is a eigenvalue problem. Here C are eigenvectors of matrix A and lambda are eigenvalues of matrix A. So, for the solution we must know only the matrix A, and any means we can get the eigenvector and eigenvalue of that matrix. Then we can write the solution. Let us say all eigenvalues are real and different. So, there will be three cases. The case 1, that all eigenvalues are real and different. Second case, eigenvalues are real but same, identical. The third, eigenvalues are complex, conjugate complex basically. So, for each case the complementary solution will be different, and this has been already explained in the book of mathematics or in the paper of 3-dimensional solutions where first order differential equation is solved. So, present case I will write, let us say for the case of eigenvalues where eigenvalues are real and different, in that case we can write the solution ZC complementary solution will be, let us say y11 e raised to power of lambda 1 of x plus y12 e raised to power of lambda 2 of plus y3 e raised to power of lambda 3x plus y4, either generally we call it C. So, basically it will be C11, C12, C13 and C14 and so on, and C110, 110 we can write like that, comma 10 e raised to power lambda 10x. So, lambda 1, lambda 2, lambda 3 up to lambda 10 we have a 10 eigenvalues and corresponding eigenvectors. So, ultimately the complementary solution can be written as a matrix C which is having 10 cross 10 and E lambda x, which is a diagonal matrix of 10 cross 10. So, in this way the complementary solution can be find it out. Now, the concept of particular solution. It depends on the type of loading. If you remember, just I would like to explain with the help of a simple example. So, this function, that how do we assume a particular solution, if it is a constant or it is a function of x or it is a function of a sine or exponential, the same way we assume a particular solution of that thing, let us say C1 of x plus C2, any constant, you can say instead of a C put D1 and D2. So, same way if our loading is uniform, UDL loading, so for that case that ZB will be minus of A inverse and Q. That is our for the case of a UDL load. But if load is something else, so we have to evaluate the particular solution. So now we can say that total solution will be C a matrix and e raised to power of lambda x plus some arbitrary constant that we can say that, let us say R1 and R2 ZP is known to us. So this is the arbitrary constant. There I did a mistake, that a constant will also come up here, any constant, let us say, previously I have written in terms of R. So a constant R1, R2, these constants will also come into the picture. R1 will be difficult, let us say Q is also S1 and S2 and S3 and so on. So these are the constant comes into the picture when we write a solution. So these constants S can be found out by implementing the boundary conditions. If I say that along x is equal to 0 and x is equal to a, x is equal to 0, let us say, is clamped. So for that case, our variables u1 0, u2 0, w 0, psi 1 and psi 2 will be 0. So we can make a solution matrix. Let us say it will come up z1 0, z2 0, z3 0, all 0, and putting x is 0, we will get these 5 variables at, and then x is equal to a, when you put x is equal to a, maybe some other boundary condition, or again you can say clamped, so another variable. So at x is equal to 0, there will be 5, and x is equal to a, there will be 5 again. So it will be 5, 5. So a new combination comes up into there. So from there, this x1, x2 can be S1 to S10 can be solved it out. So arbitrary constants can be find out by subjecting the boundary conditions in this equation. So once we know the boundary conditions, we can sort out and final solution can be written like this. So in this way the problem is solved for the case of a Levy when it is having transverse load. For the case of a free vibration, there will be no load. So in that case, Z matrix, so comma x can be written as A into Z. There will be no loading. So it will be only a homogeneous solution. Again we can assume a solution like e raised to power of lambda x into c z, and finally it becomes lambda I minus a c times of lambda x is equal to 0, and then finally we write a solution of z is equal to C matrix into e raised to power of lambda x into some arbitrary constants, but here no particular solution is 0. So subjected to the boundary conditions, if we subject all these boundary conditions, let us say this is M matrix, right hand side will be 0, and in this M we have a omega term is there, omega square is there. So we do not know the natural frequency of the system. So we have a system like this, M S equal to 0. So a homogeneous equation. So the S1 non-trivial. Trivial solution is that S1 is 0. So, if all constant is 0, what is the fun of doing these things? So, S1 cannot be 0. So, we will try to say that if non-trivial solution is possible only when determinant of M is going to be 0. So, in this matrix there is a omega. If we put a determinant of M is equal to 0, so it leads to a equation that is known as character sketch equation. So, we solve that equation through a iterative process, or if you can directly solve, because these days some algorithms are available in the MATLAB that you directly, if you give this character sketch equation, they will give you the roots, or you can write the code. So, generally if it is a omega square inside that equation and we do not know the omega, then what we try to solve through substituting initial guess, that if this omega, so let me write, it may be like that. So, lambda 1 times of 10 square and 10th root and omega square, sometimes somewhere it will be 9, I do not know, 8 times C1 C2 and so on equal to 0. So, the equation will like this. So, if omega is the solution of this equation, so it will satisfy this equation, otherwise it will not satisfy this equation. So, we assume, let us say W is 0.1, 2 and 3, and then we through iterative procedure we find it out. So, there are some algorithms in which we can find out the solutions by processing that, moving from initial guess to final. So, generally for these cases we try to take guess from our simply supported, or for example that a simply supported shell will have higher natural frequency compared to a clamped. So, we have to reduce the guess so that we can get the frequencies. This is the technique where the boundary conditions are to be satisfied in the displacement form. So, basically if we say that my cylindrical shell is free, in that case nxx need to be specified, or n theta theta, nxx and mxx need to be specified. So, present case we do not have a variable of nxx, mxx. So, we need to satisfy in a average sense, that we means nxx in a further using the concept of constitutive relations we satisfy. In the lecture L1 week 6, I have said that the mixed form in a extended counterweight method, a mixed form is used. Similarly, for the case of a Levy solution, mixed formulation can be used. In that case, we assume that nxx, mxx are our variables, and then using the 5 equations from the cell constitutive relations and 5 equations from the PDE and or maybe some more variables. So, we can solve and then ultimately they also form a first order differential equation and we can solve the problem. Only advantage of using mixed formulation is that boundary conditions are satisfied exactly, but in the present displacement base, that nxx, mxx are not our variables. So, using the constitutive relations they are satisfied. So, accuracy point of view, in general there is no difference, only difference comes up maybe near the support at the very edge. If you plot a circumferential variation along that at very clamped edge or at very free edge, then some boundary effect may appear. So, to accurately predict that behavior, the mixed formulation is preferred mostly. So, with this I have explained that how to develop a Levy solution for a circular cylindrical shell for static bending case and free vibration case. Thank you very much.